Okay, well, welcome to the Friday afternoon colloquium. So our speaker today is Dr. Eduardo Ibarra Garcia Padilla, so hopefully I got it mostly correct. So he's actually a colleague and visitor of our own Tori Vitale, so thanks to Tori. Brief academic history. So Eduardo, that's what I was just finding out. Eduardo actually did his undergraduate at UNAM, and so actually over dinner I'd like to talk to you because one of my colleagues is looking to get a position there. So I spent like a summer there, and it's fantastic. I love Mexico City. And then he did his PhD at Rice University, and actually he's now a postdoc shared jointly between UC Davis and San Jose State University. So I also want to hear more about that, since I mean CSUs should have postdocs and actual research postdocs. And so I'm interested to talk, many things to talk over dinner. Anyway, so he's going to tell us about quantum simulations of the Hubbard model, higher symmetry fermions, and nuke architecture. So welcome, Dr.
Thank you all. I would like to say, if you have any questions throughout the talk, feel free to answer them. If I feel like they're going to take a long time to respond, then I'll just say, well, let's chat after the talk. So yes, thanks for having me here. And I would like to start by saying that in nature we have a lot of different solid materials. So for example, we can have good conductors like copper. Or we can also have good conductors of heat like a pan. But we also have good insulators, both either electric or thermal insulators. And we also have materials that have magnetic properties. So a natural question to ask is, well, why all of these materials have such properties? Well, let's start by what is a solid. So here I have a picture of a chunk of, I think it's lithium. And if we zoom in, what are we going to find out? We're going to find out that the ions are organized in a periodic array. And this here we also have electrons that have spin up or spin down. But the thing is, like we don't have just one or two. We have 10 to the 23. So even in a very small piece of lithium, we have a lot of atoms. So just to put this a little bit more on like a line of thought, what we have for a solid is a periodic array of ions, or a lattice, and then we have the electrons that I denote here by red and blue. And these electrons have two things. They have kinetic energy. So what this means is that the electrons can move around the lattice, and they also exhibit or experience Coulomb repulsion. So what this means is that the electrons have charge and they repel each other. And finally, the other ingredient is that electrons also have a spin. And that's why I denoted them here by red and blue, or up and down. And just to keep having this number in mind, there's 10 to the 23. So this is a many-body problem. There's many of them. And with these three ingredients, well, actually four, so kinetic energy, spin, interactions, and a geometry, we have this myriad of systems that can exhibit different properties. So like metals, insulators, magnetism, superconductors. So how can we understand the solid? Well, we can write down the Hamiltonian, and what we have here are all the terms that, in principle, if we could solve this problem, we could say what's going on with our solid. However, since we have 10 to the 23, this is pretty much impossible to do. So it is a very hard problem to solve. On the first hand, there are no analytic solutions available. So if we just sit down and write that Hamiltonian and say, hey, solve it, well, it's not possible, except in very, very few cases. And on the other hand, like numerical solutions face exponentially growing Hilbert spaces. So even though if we would like to solve this problem for the 10 to the 23 particles, we will not be able to do so. We're limited to small systems. So just to remind us what we're after is the fact that we have a lot of interesting materials on the left-hand side, and then we have different building blocks. And what we would like to do is construct a model such that we can reproduce some of the properties the real materials exhibit. So what we're after is not the specifics of different materials, but we're trying to capture the essence of strongly interacting systems. One of such models is the Fermi Hubbard Model. So for those working with Ettore, they probably know what the Hubbard Model is. So what we have here are the electrons, that I would denote by red and blue balls, living in the lattice. And then the first term contains the kinetic energy. So what this first term here is saying is that if we have a particle with a spin sigma, for example red, on site I, it can hop to site J with an amplitude T. And this is just limited to nearest neighboring sites. Now, when we have two particles with different colors occupying the same site, so this red one hops here, that will raise the energy by an amount U. So this emulates the Coulomb repulsion. And finally, we can control the density of fermions by changing the chemical potential. So with this, we have the kinetic energy, we have the potential energy, and we can control the filling. So one could think, well, this is a very simplified model of what this solid is. However, it reproduces the physics of interesting materials such as the cuprate, cuprates. So this simplified model exhibits an antiferromagnetic phase, strange metallicity, and there's some questions of if it captures the superconducting phase there. So what we would like to do is, well, we have this very nice model. Let's try to do it in an experiment. And this is where the field of quantum simulation and atomic physics comes into play, where we make an analogy between the solid state system, where we have a solid crystal, and we have the periodic potential made by the ions in blue, and the electrons in yellow. And then, in the experiments that are generally in the basements of the universities, they generate periodic potential made by optical interference, and I'll talk about this in the next slide. And then they put atoms into this potential. So what we have now is a system that emulates what's happening in a solid crystal. And the reason we're very excited about these things is because these are very clean systems. We do not have imperfections or chemical substitutions. We have a high degree of control. By what I mean with this is that we can change the depth of the lattice, we can change how the atoms interact with each other, and we can change the fillings. And finally, we have access to precision measurements. Like we can take, for example, a snapshot or a photograph of the configuration of the atoms in the lattice. So just to give a very brief explanation, the optical lattices are made by the interference between two lasers. So we shine light, and then this gets retroreflected, and we generate this periodic array. It's a standing wave, and the atoms get trapped in the nodes of the system. And then we can do it in 1D, or in 2D, or in 3D. So a natural question to ask would be, okay, that's really nice, you can do this in experiments, but why does the system have to be ultra cold? And for those that have seen the Avengers movies, they're familiar with this scene where the Ant-Man is explaining about the quantum realm, which I just think was pretty fun. So the question is, in order to see the quantum mechanical effects, we need to go very cold. And if D is the average spacing between different atoms, what we need to do is cool below, cool down so this quantity, the Broglie wavelength, is of the order of the spacing. in such a way that we see the wave-like behavior of the particles we have. And just to give a scale of how cold the systems are, if we make, if we draw this line from Buenos Aires to this city in Canada that I don't remember its name, Vancouver, thank you. This is like 11K kilometers, and the tip of a pencil is around 4 millimeters. So if we translate this like in temperatures, this would be like, let's say, room temperature 300 Kelvin, and ultra-cold atoms are around 50 nanokelvin. So there are many orders of magnitude of difference when these experiments are realized. So let me move on to this next slide and talk to you about what the experiments have done so far. But before we go into that, are there any questions so far? Especially from the students? We're good? Okay. So what I have here is a cut of the phase diagram of the SU2 Fermi Hubbard model. On the y-axis we have the temperature, and on the x-axis we have the doping. And by doping, this means that we remove some particles from the system. The stars here and the lines correspond to what different experiments have done in recent years. So most of them start around like 2013, and I think the last one they had here was like 2020. So these things have been done in 2 dimensions, where people use a quantum gas microscope. So here we have the quantum simulator, and experiments take a snapshot or a picture of what density profiles look like. And you get an image like this, from which you can reconstruct, and you can see, for example, this checkerboard pattern that corresponds to an antiferromagnetic phase. Experiments can also be done in 3D. This is from the group of Randy Hewlett, where they also, well, they have to use different techniques to access this type of correlations. But what I want to bring attention to is that all of these results are above this box that I just drew there. So even though they are like ultra cold, with respect to the energy scales imported in the model, these systems are still very hot. So what we would like to do is, how can we have the experiments probe this region where one would expect to see, well, this antiferromagnetic phase, pseudo-gap, like the possible superconducting in a dome. How can we do that? And this is where the research that I conducted in my PhD comes into play. So on the first hand, we have the higher symmetry fermions, or fermions that exhibit this SUN symmetry. And you'll see in a few slides why I picked that Rubik's Cube with so many colors. But just to give like a milestone, with this, the experiments have achieved the coldest fermions ever created in absolute temperature. And another route is to go and use the optical tweezers, where the lowest entropy particle fermions were ever created. So for the sake of time, we'll talk mainly about the SUN fermions. So what does this mean to have this generalized Fermi Hubbard model to n components? So if we look at the figure I had before, we only have red and blue particles. Now we're going to have red, blue, green, yellow, orange, etc. What we've done is we generalized the Hamiltonian that we're using to describe the system to n components. So now this label sigma runs from 1 to n. But the important thing here is that all the parameters, such as the tunneling, the interaction strength, and the chemical potential, do not depend on which of these colors we pick. And in order to have the different colors, this corresponds to different spin projections of the atom that we are using. So if we look at the periodic table, and there's also one over there, the atoms that are being used are the strontium 87 and ytterbium-173, which have a large nuclear spin, in this case 9/2 and 5/2. So why is this important, or why do we have this SUN symmetry? Well, this is because of how the different atoms interact with each other. So if we have an alkali, like lithium or hydrogen, in this case we have hyperfine coupling. So what this means is that the nuclear spin gets coupled to the angular momentum. And what this translates to is when we have a collision between two of these atoms, or when they interact, these collisions do depend on the nuclear spin. In other words, they depend on what the projection of I is. On the other hand, if we have an alkaline or alkaline earth, like ytterbium or strontium, the electrons are in a singlet state and do not care about what the nucleus is doing. What this means mathematically is that there is no hyperfine coupling between I and J. When two of these atoms collide, these collisions are independent of the nuclear spin. They're independent of what the projection of I is doing. And this is what gives rise to the SUN symmetry, where N just corresponds to 2 times I plus 1. So for ytterbium, that was 5/2. You can go up to SU6. For strontium, was 9/2. You can go up to SU10. And what is really nice is that in recent years now, starting in 2016, experiments have started to load this atoms of ytterbium into lattices, and I start exploring the SUN Fermi Hubbard model. So like, for example, here there are plots of like the density as a function of chemical potential, nearest neighbor correlation of functions in strongly dimerized lattices, and more recently, and this is part of my work, how does these correlations depend on the value of N and the dimensionality, and in particular getting this, the coldest Fermi gas in an optical lattice. Are there any questions so far?
So
yes.
On the right figure, you have like SU6 1D, SU2 2D, SU6 3D. I mean, is it very technical, or what's going on?
Oh yeah, so we'll go through that in the future slides. But
okay.
yeah, essentially, here they measure like nearest neighbor correlation functions for a system in 1D, either in green and blue. The green corresponds to the SU6 symmetric, so we have 6 different colors in the lattice, and the SU2 to just 2 colors. And then they also measured how these correlations for a given N, like the SU6, but now in 3D. So, and we'll discuss this plot in the future. Yes?
I didn't quite catch why there was no hyperfine coupling between, or in the alkaline elements.
So in the alkaline element, you have two electrons. So, for example, in hydrogen you only have one, right, in the valence. And for the alkaline you have 2. But in the ground state, this comes in a singlet state. And what this means is that the total angular momentum of that configuration is 0. So you have a spin 1/2, spin 1/2, but then the total J is 0. And the hyperfine coupling is given by I dot J. So since J is 0, that means that you can pick any MI projection. Thank you. Okay, so I would like to motivate, like, why should we be interested in studying this SUN system rather than just, okay, yeah, we can put more colors, good luck. I like this phrase that I found in a book about symmetry, that they say, like, the superiority of a symmetrical flower is reflected on a greater production of nectar. And that nectar has a higher sugar content. Symmetry tastes sweet. And the SU2 system is a sweet one. It has a rich phase diagram. It has a strong correlations in both the spin and the charge channels. It has canonical phases of matter, strongly correlated systems, such as this like high temperature group rates. But the SUN might be even sweeter. Like, we can have other types of ordering. We can have this very peculiar types of valence bond type of structures. There are some predictions that one might have a spin liquid. And the thing is, like, we're not limited just to changing n, but we can introduce some anisotropy, we can change the interactions, we can introduce doping into the system. And for SU2, we sort of know what to expect. It has been studied very thoroughly, but we do not know what to expect, for example, when we go to larger values of n. So this is where we jump in with the quantum simulators, and what we're trying to do is to do a similar mapping of what the phase diagram should be. So what I focus in the rest of the talk will be what happens when we are at 1 particle per site, like on average on the site, and then we just change or lower the temperature and change the interactions. And just to give an idea of how hard the problem is to solve, when we wrote this Hamiltonian, it seems that the only thing that we've done is change the sigma to just run from 1 to n, like just added more numbers. But the thing is, like, that translates into making a very hard problem numerically. So if we fix like the number of sides on the lattice, but we vary n from 2 to 6, one can see that for n equal 2, we have 10 to the 6 states. And this is like kind of like state-of-the-art calculations with exact normalization. So you write down the matrix and diagonalize this thing. So how are we going to deal with something that is 10 to the 12 times larger? Like that, it's a very big number. So what we have done and the techniques we have developed are, one of them is, well, exact diagonalization, but one has to be clever. Numerical link cluster expansion, DQMC. But the important thing is, like, we have to exploit the symmetries of the Hamiltonian, and we have to exploit our knowledge of the physics. So maybe in some cases we can do some approximations or simplify certain things. And so this is a little bit more technical slide, but I just wanted to share it. Like, when can we use the different techniques? Like, in which dimensions? For example, ED works best in one dimension, at large interactions. The NLC can do it 2D and 3D, also large interactions. The DQMC mainly works in small interactions, and it's ideal for like 2D or 3D systems. And this, in collaboration with Ettore here, with CPQMC, also in 2D and 3D systems. Cool. So as an outline of my research, and then here I'll ask a question to the audience, I can talk to you about two different things. We can talk about universal thermodynamics. So what we studied here was how do different thermodynamic properties depend on the degree of symmetry n. And we asked the question, are there any temperature scales that depend on n? On the other hand, we have a work on short-range magnetism, where here we wanted to understand how nearest neighbor correlations evolve with n, and how they depend on dimensionality. Do any preferences?
Both sound interesting.
Huh?
Both are interesting.
Thank you.
So, I mean, so students, no preference?
I'd go for the second actually.
The second one?
Yeah.
Okay.
I say give that.
Second? Okay. Okay, so let's think of two sites. like a lattice that only has two sides. And on the left-hand side, we have both spin up. So if we have the same spin states, what happens? I cannot take one of these particles to hop into the other side due to Pauli exclusion principle. Now, what would happen if we have different spin states, like up and down here? Well, I can in principle take the up, hop to the neighboring side, and then come back. So what this meant is when we have different spin states in the neighboring sides, the system is more delocalized because it can move around, come back. And by this virtual process, it can lower its energy. So just by this simple argument, what this means is that these fermions prefer to one-to-line. It's more beneficial to have different spin states on neighboring sides. And this argument also works for SUN. What this means is that instead of picking red and blue, you could pick green and green, green and yellow, green and red, blue and yellow, etc. So it works for all of this. So the way I got involved into in this project that is in collaboration with experimentalists was they gave us a phone call and say, hey, we have this data, we need some input, we would like to compare what you get from numerical simulations here. So what we have in this plot is, on the x-axis, the entropy per particle. On the y-axis, it's this quantity called the singlet-triplet imbalance. It's just the name of what they're doing. But what is important is that this quantity is proportional to the nearest neighbor spin correlation function. What is this quantity here is defined here on the right, and what we do is we measure how anti-aligned the neighboring spins are. So it's a way of quantifying if I have a red spin on one side, what is the probability of having another color on a neighboring side. What we have in the panel here are results for SU6 in a 1D chain, and for SU2 also in a 1D chain. So in blue, SU2, in green, SU6. So what can we see first here? The first thing that I notice is that if we make a horizontal cut, correlations develop at higher entropies for larger n. And the other thing that we can notice is that if we make a vertical cut, is that these correlations get enhanced for larger n as well. So let's try to understand this with a simple physical picture. Let's imagine we have this 1D chain where we have one particle per side. This is called the Mott regime. And now let's assume the interactions are very large, so that there are no charge fluctuations. In other words, these guys do not like to hop to the other side. So in this case, what is the minimum entropy we can have without having correlations? Well, the answer is log n. What this means is for a given site, we can pick any of the possible colors. So if the minimum entropy without spin correlations is log n, what this means is that when we go to lower entropies, we necessarily need to start developing correlations between the sites. So if we make like a cartoon of this, this illustrates that for an SU6 system, when the entropy is around log 6, then we should start seeing how correlations develop. So with that argument, we can sort of understand why that happens. So what we did then was we performed numerical calculations with ED, so we diagonalized the full space, and we obtained the solid curves. So we have a blue curve here and a green curve here. And the important thing here that I would like to share is that we didn't fit anything. The experiments just told us, oh, we're doing these experiments at this interaction strength of 15.3. These are the trap parameters of the experiment, and that's it. We didn't fit any of those things. And we can see that there is good agreement between the data. I mean, it's not perfect, but there's fairly good agreement. But the most important thing for us was we can also reproduce the same trend that the experiment is seeing. Correlations develop at higher entropies, the larger n, and also they are stronger for a given entropy per particle. So we were really excited about this. And then they said, well, we also have some data in 3D. So the 3D data corresponds to the red markers that we have here. And as I said before, we cannot do exact diagonalization in a 3D system. It's just too big. So what we did here was determinant quantum Monte Carlo simulations. And those correspond to the dashed lines here. But, and I hope this is not too discouraging, but what we saw was that we couldn't go below this entropy. And the reason for this is because we have something called the sign problem in numerical calculus, in the DQMC. So when we reach temperature, I think it's around 1 times the tunneling, the data just becomes very noisy, and integrating around there just gave wrong results. So the results with DQMC cannot go to lower entropies, but the experiments can. So this is like a prime example of quantum simulators as experiments to probe new physics. But it also opens the question for us, how can we tackle some of these problems? Can we develop other numerical techniques? How can we mitigate some of these problems? And an interesting thing here too is, well, the way experiments are performed, they do not have access to entropy. No, sorry, they do not have access to temperature. They only have access to entropy. So if we would like to know at which temperature the experiments are operating, what needs to compare with the theory? So what we did here was, if we compare the largest spin correlation that was measured in the experiment with the theory, we can extract that the temperature at which it operates is around 0.1 times the tunnel. And the interesting thing here is that the previous lowest temperature in one of these experiments was 0.25. So we are 2.5 times colder than the previous record. If anyone is curious and wanted to translate this to actual numbers, this corresponds to a temperature of around 1 nanokelvin. So this thing is crazy cold. It's colder than outer space by a lot. Yeah. Are there any questions? No? We're good? Okay. Yeah, so I have actually, since we have time, I'd like to talk a little bit about the other project that we found very interesting results. So we have talked right now about magnetism in the system. Now let's talk a little bit about the thermodynamic quantities. So what the predictions are in the ground state in 2 dimensions is that for SU2, one has this checkerboard pattern. So it's a 2 sublattice order. We have blue, yellow, blue, yellow. Oh. Yes, sorry. And then, as I previously said before, what we know is that these fermions prefer to anti-align. So what one would expect for SU3 is that we also have some sort of sublattice structure. This is called a true sublattice structure. So we have blue, then red, then yellow, then blue, red, yellow. And it alternates like this. But the thing is, like, there is no simple trend with what happens to the ground state. So for SU4, the predictions are we should have this dimerized pattern, and for SU5, one has this, like, it looks like a square thingy, but it's another type of ordering. So the important concept here is that there is no simple trend as we switch n. So what we wanted to answer was like, okay, can we understand the trend with n at a finite temperature? So if we start very, very hot where there are no correlations whatsoever, and then we lower the temperature, can we say something about the n dependence of quantities? So what we focused on here was, if we vary n, vary the interaction and the temperature, but we fix the density, what can we say? What we see is that at temperatures above something called the superexchange energy, which corresponds to the process of being able to hop to the neighboring site and come back, the system is just dominated by short-range correlations, like the ones we previously discussed. But what was very surprising is that when we rescale some of these quantities, curves for different n obey a simple functional form. And that is very surprising. Because one rarely says these types of simple features or scalings in strongly correlated systems. So let's make this more functional and give an example. What I am plotting here is the energy as a function of temperature for the n=2 system. We can see this nice monotonic curve with t. Now, when we present the results for SU3, that are the light blue, we see that we also have a similar structure, this monotonic curve, and there is a crossing at a finite temperature. SU4, same story. SU6 as well. So all of these curves present a crossing in this very narrow window of temperatures that corresponds to this black line. So we were like, okay, if I have two curves crossing, that's not very hard. But having four of them crossing at the same point, something else must be going on. So what can we understand this in a simple way? So we propose the following. If the energy as a function of temperature and n is given by an expression where the first term only depends on temperature, and then the second term, the n dependence is captured by this simple functional form, then the following should hold. If we subtract this term to the left-hand side, we have this function that we call d tilde. This quantity should be independent from n, because then we should recover this, just this term over here. So we said, okay, let's test it. We took the data I previously showed to you. That looks like this, the curves as a function of t for different n. And then when we calculate e tilde, all of these curves collapse on top of each other until we reach this vertical scale that corresponds to the superexchange energy. And then they split apart. So one could say, well, you were lucky, that only happens for that value of the interaction of A that you picked. But no, that's not the case. When we plot for different panels, and I know there's a lot of curves, so this is just to illustrate that we can vary it from u=4, 8, 12, and 40. When we compute the quantity at e tilde, all of these curves collapse, and here we just zoomed in to illustrate where it starts breaking down. They collapse on top of each other until they reach the corresponding vertical line in each case. So there is this collapse up on a single curve upon the rescaling, even though 1/n is not necessarily a small quantity. Like 1/2 is not that small. So this was really exciting. We're like, okay, can we understand a little bit more what this means? Well, taking a look at one of the panels, what we have here are the solid lines correspond to the QMC or NLC data. The dashed lines correspond to something called a second order high temperature series, which is a perturbative approach. And the dotted line corresponds to a second order NLC. And I'll explain in a second what this means to clarify. So in the high temperature series expansion, what one does is a perturbative approach in the tunneling over T. So what one would expect is that that approach should fail around a temperature of 1 times the tunneling, because then it's no longer a small parameter. Like if you think of the Taylor series, and you say, well, I'm doing a Taylor series x plus h should be small, right? So what we see is that the scaling is obeyed. All the curves collapse on top of each other in the dashed line, but they do not reproduce what's going on with the solid lines. Like the solid lines keep going down while this thing is diverging going up. So we're like, okay, that's not a good explanation of the phenomenology. Now, if we take a look at the second order NLCA, what this means is you solve the problem in one side, then you solve the problem in 2 sides, and then you do a linear combination of these results. And what we see is that those which correspond to the dotted lines obey the scaling and nicely reproduce the curve over here. I mean, the scaling still holds down below the vertical line. So what that means is that this scaling is breaking down where longer range correlations start to develop. And why is that? The dotted line corresponds to, if I'm only solving on 2 sides, I can only have correlations between 2 sides. So necessarily that means this picture, or when the scaling starts to break down, is when we develop longer range correlations. And the very nice thing is that this understanding holds for all the values of u over t considered. So for small u, for u equal 8, 12, and 40, the dashed lines fail to reproduce what's going on, but the dotted lines nicely follow the results. So what we found in this project was that for temperatures above this super exchange energy of the vertical lines, these very different models exhibit a simple universal behavior. And so, yeah, when one goes to lower temperatures is when you start observing this very peculiar patterns that are unexpected. And sort of to connect with experiments, since many of the students, they ask me about like theory experiment comparisons, this things is something that we observed before, and then we share the results with experimentalists. And now what they're doing is they're using some of our data that are the solid lines to fit to the experimental data they're measuring. So in blue we have the density, and in green we have something that measures the number of occupancies on a given site. So either if they have 2 or 3 or 4 atoms on a single site. So yeah, and I think as you can see there's pretty good agreement between the theory and the experiment. So with that, let's end the talk. And so I want to give like a big picture summary. So the field of quantum simulation, it allows you to explore these toy models like the SU2 or the SU and Fermi Hubbard Model. And these models, what we aim to is to capture the basic ingredients of the solid materials and understand strongly correlated matter. And well, some of these materials could have possible or interesting technological applications. And when we go to larger spin, when we go to this SUN and have more colors, when they are sufficiently hot, the systems have a universal behavior. And the other thing is that system with higher spins get colder. Like this 0.1 times tunneling story I told you, with the coldest fermions ever. So now to mention a little bit about each specific project. For this universal thermodynamics, what we found is that different thermodynamic properties like the interaction, kinetic, and total energy have a simple dependence above this energy scale J, and that this simple scaling it can be explained by a two-sided calculation. And on the other hand, for short-range magnetism, we found that antiferromagnetic correlations are stronger for larger and lower dimensions. And now this opens questions of what occurs with longer range relations. Are there order phases? So just to sort of illustrate where are we going to is if the orange line denotes what I talked to you today, I drew two lines here. What we're exploring now is what happens also at t equals 0, and this is where Ettore help has been amazing with the CPQMC. And then we also would like to go what happens when we dope the systems, both at t equals 0, but also at finite temperature. And here I have some results, for example, on an SU3 system, what happens to spin correlation functions, the structure factor, as we lower the temperature. So just sort of to illustrate kind of like what kind of directions we're pursuing now are with in the ground state calculations, can we understand quantum magnetism as a function of U, doping, and N? And can we improve the trial wave functions using neural networks? That's something we just were talking earlier today. And of course, my collaborators, Ettore, Shunhan Feng, that this is not Flatiron, my PhD advisor Kevin Hassard and Richard Scalator at UC Davis. And then another project that I'm working on has to do with an interesting geometry called the 150 Fleet lattice. We're trying to map the phase diagram and might have interesting connections with some of those optical tweezers that I just briefly mentioned, with Sankatami at San Jose State and Wasim Baker at Princeton. And of course, it's always nice to put some beautiful pictures of all the collaborators. My advisor, Kevin Hassard at Rice University, Richard at UC Davis, the grad students in the group, so Hale, Hao Tian, Ziwen, Kevin was an undergrad with us, and Shunhan, and you know him, right? And on the experimental side, the group of Shintaro Tai and Yoshiro Takahashi in Kyoto, and the group of Simon Folling in Munich, doing some of this work. Thank you.
Thanks for a great talk, Eduardo, and we have time for questions now.
Yes.
Okay, I want to ask you about the patterns you're discussing. So the patterns form in like equal in a thermal equilibrium.
Yeah. Those are in thermal equilibrium.
Okay.
Also, they're t equals 0. Just they're ground state calculations.
At finite temperatures, patterns do not emerge, or
Yeah. So the question is like at finite temperature, what types of patterns could survive? So for example, let's forget about a second about the Fermi Hubbard. If you take an Ising model, then you have also spin up and spin down, and you turn on temperature, what happens? Imagine you're fully magnetized, and then you turn on the temperature, you're still having thermal fluctuations that start breaking some of this correlation, right? And actually what you say is that the critical temperature is T equals 0 by the Fermi-Wagner theorem. Because you cannot break continuous symmetries. But now going back to this Fermi Hubbard model, can we see some signatures of the orders emerging? So instead of thinking of going from T equals 0 and heat it up, maybe what at which temperatures can we start observing some of this phenomena occurring as we lower temperatures. So yeah, I would expect like we should see some of these things. I mean, there will not be, some of them will not be truly long-range order because that can happen in some cases. But yeah.
Thank you. Can you also talk about the operator that allows you to figure out that the patterns emerges?
Oh, the structure factor? This one?
No. The previous, it was that one.
Like this one? Yes.
Is this the one that you use to figure out that like the nearest neighbors are not aligned?
Yeah, so what this is measuring, there are essentially two terms. Forget about the sum for a second. So what this is saying is, okay, on site I and I plus 1, so the neighboring site, what is the expectation value of having the same spin? And then what we do here is we subtract the sigma tau. So let's say we ask red, red, and red, yellow. And then what we have to do is we have to sum over all possible contributions to this quantity. So you can think of this as a generalized quantity of the SC correlator, but for more colors. So yeah, it does in a way just measures how anti-aligned the neighboring spins are. So I don't think I have any plots here, but if we look, for example, at the yeah, I think this will work. At this SU3, well, actually, like SU2, what happens to the correlation function? So first it's positive on a given site, and then it should be negative, because you have up and down. And then it becomes positive again, negative, etc. Now, what would you expect for this SU3? Well, it's blue, blue on one side, and then it should be negative and negative on the two next sides, and it should become positive again. So we have some very nice results actually on the SU3 in the ground state with the civic UMC, where you can see how this correlation function depends on distance. And yeah, so
what it gives is a number, right?
yes.
How does it like the number gets interpreted? It's like if it's 0, there's no correlation.
Yeah. So in this case, yeah. So what happens when you're at very high temperatures? There are no correlations. So in that case, this expectation value just becomes the product of the expectation value. So it would be n sigma and the n sigma on the neighboring side. And that's just measuring the density on the two sides, and it should be equal to this. So it just goes to 0. So when you're uncorrelated, this number is 0. When you are correlated, it goes to 1. Yeah, well,
Students, question? Because I'm going to ask a question, but you guys should ask first. Okay. So, Eduardo, if you did SU2 in 3D, so the general trend is like the higher SUN, it basically starts to go up earlier in 1D. So if you did SU2 in 3D, what happens? Does it actually start to go up later than the SU2 in 1D, or?
So for example, if we had the SU2 in 3D, it should lie around here, like below the SU2 curve. So like for example, the red and the green, the correlations kind of sort of start developing around the same area, but they're just lower in magnitude. So it would be a similar story. If we put the SU2 curve, it should lie below the blue in 3D.
So conceptually, why as you go to higher dimensions, do correlations come up later?
So yeah, that's a very good question. So one way that I like to understand this is if when you are, for example, in 1D, there's only another neighbor. Well, actually, two neighbors. So the coordination number is 2. You can talk to the right or to the left. But then, let's say in 3D, now you have 6. So you have left, right. Oh, that's right. So if you have, so at a given temperature, there are just more ways to tunnel from one side to the other and form these double occupancies that suppress the correlation functions. So the way I understand it is that, so a fixed temperature is just for a larger dimensional that you have just more channels to start disrupting correlations. But this is also important because in 3D, you can have finite critical temperatures, right? So it's like a competition between. Okay, maybe the correlations can be a little bit stronger in 2D, but we know that long-range order cannot fully develop in 2D. So, but these experiments honestly don't really care, because what they do is like, well, if the order just spans my system, that's good enough for for us to sort of talk about ordering. But yeah, that's a good question. Yeah, anything else?
Okay.
Physics, graphs.
That was a great talk.
Thanks.
As a student, it was very nice.
Thanks.
All right, that wasn't really a question, but much appreciated. Okay, so any other questions or comments? All right, well, if not, let's thank our speaker once more. And then if you guys, were shy and wanted to ask more questions, feel free to come on down, and I think there's some more donuts left. So.